Hello. Today in this webinar, we will be highlighting designing PCBs for the Internet of Things. So hello from sunny Florida, here at RF Laboratories. My name is David Zima, and I have the privilege and pleasure of speaking today on wireless design and IoT, or Internet of Things. For the past 25 years, I've enjoyed helping other developers of wireless devices to market by assisting in the design process. This has typically included design, layout, test, optimization, regulatory compliance, as Molly stated. I'm excited today, though, to cover the exploding area of IoT development and its associated design challenges. There are a few companies that I've worked with and continue to work with. RF Laboratories is our principal, and Radios Inc. is another company that supports some of the designs that we have developed. So designing electronic products with the Internet of Things capabilities is no longer the exception, it's the rule. IoT technology not only opens up numerous new product categories of electronic devices, it drives innovators to rethink the ways that consumers interact with traditional techless products. So from makers to startup companies and beyond, the opportunities to invent new tech devices and reinvent existing products with IoT capabilities, from health trackers to thermostats, are seemingly endless. Electronic design is no longer just schematic capture. Some of you have been in the industry for a long time, 20 or more years. It was schematic capture and layout, but now PAD's product creation platform integrates many of design tools needed for IoT designs, leveraging the capabilities from Mentor Graphics, the largest EDA supplier for printed circuit board design. PAD suites provide a range of capabilities from schematic capture and layout to simulation analysis. And for specialized design requirements, there's a range of options available, from DDR, timing analysis if you happen to work with memory, DC drop power integrity simulation, advanced high-speed routing, RF design, and advanced FPGA optimization, just to name a few. So let's start with what is the Internet of Things. Since today's topic is IoT, let's begin with a brief description. IoT stands for the Internet of Things. It has given rise to the demand for good RF design practices, from the wall outlet power all the way to the antenna. It has also increased the need to understand what design requirements will comply with regulatory certification and what oversights may lead to failed tests at the FCC and CE labs. And as you can see from this graphic, the number of IoT devices have really just been growing year after year. You have devices such as wireless mousetraps now, wireless HVAC registers, and the list just goes on and on. So there are several IoT standards being employed today. You have Zigbee, which we all are familiar with, and Bluetooth, which has been around for quite some time, named after the old King Harold Bluetooth, united the Scandinavian kingdoms many years ago. We also have Z-Wave, which has really exploded, over 200 million products in the field, and there are several other standards. One thing that these standards all have in common is they have the same design requirements. They all follow the same laws of physics, and they share the same practices, and unfortunately offer the same pitfalls for people who don't, and designers who don't follow those practices. They also get more demanding as the frequency increases, which is something a lot of designers don't consider. For example, with Z-Wave here at 900 megahertz, it is a little more forgiving, not much, than working at 2.4 gigahertz with Bluetooth. So mains to DC to power an IoT device. Today we will be starting at the wall outlet, or mains as it's called. The mains power 120 volts AC. Now, many IoT devices plug into the wall and derive their power from the AC outlet. There's a very useful tool available by Mentor Graphics as a starting point for such a design. As an example, PAD's analog mixed signal, also known as AMS, is available in the PAD's designer schematic. So we have a very simple circuit here with a wall outlet plug that goes into a rectifier and filter and gives a DC output voltage here. And the process we follow is capture, simulate, optimize, and verify with this tool. So if anyone's familiar already with PADS Logic or Mentor's Designer, this will be a very intuitive transition to AMS for you. So let's analyze this simple circuit that is intended to provide about 1.35 volts power all the way up from 120 volts AC. A nominal simulation with PADS AMS shows that this circuit would supply the needed voltage, but the values of the components used in manufacturing the product can vary. In the schematic, the resistors are specified to have a tolerance of 10%. So this would be a one-pass simulation showing nominally 1.35 volts, and it would be set up in a simulation control window such as this. Now, a 10-pass Monte Carlo analysis shows the output voltage varying from 1.27 volts to 1.48 volts. This may be outside the acceptable range of output voltage that the IoT device may require. A regulator might solve this problem, but if we were looking at using this for an analog to digital conversion, we might need a voltage reference to obviate this this irregularity in voltage. So we could solve the problem by specifying tighter tolerances for all the resistors in the design, but this may not be necessary. We can quickly do a sensitivity analysis, alternatively, of this result showing that the circuit is most sensitive to R16. We can change the tolerance of R16 to 1% and rerun the simulation. The results are not as good as we would like. The second pass shows a sensitivity to R12 as well, so we change the tolerance to 1% for R12. Repeating the 10-pass Monte Carlo analysis one more time, now the output voltage is in a much tighter range. Cost is always an issue with IoT devices, and we were able to quickly determine that we only needed to change the more expensive 1% components for 2 out of all the resistors. And as we know, in very high volume IoT products, such as ones are going to be released at Home Depot or Lowe's or in other markets, just saving 1 penny of cost with a sale of 1 million pieces a year can save $10,000 in component cost. This is a typical design with associated steps, the additional wireless functionality that many IoT devices place on the designer after capture and simulation is the RF layout. Now, this is commonly where the trouble begins, and I know that's why a lot of you logged in today to get a sense of what you might do to try to avoid some of those pitfalls. So RF design has been called the black art due to its ostensibly mysterious and elusive nature. I'm here to tell you that RF design is not mysterious. It follows the laws of physics like everything else in the natural world. However, RF is very unforgiving of oversights and unfortunately rich in pitfalls. So here's a representation of a far field simulation graphic for an isotropic antenna radiation pattern. And an isotropic antenna is like the type that's on your automobile, just a wire sticking up with a ground plane under it. So notice the holes or nulls, as they're called, right here. This is what gives RF the black art reputation, is that radio waves don't always behave in the way you'd like. And of course, on the circuit board, there is radio waves being generated and currents and voltages through different structures that create interference and also are sources of signal loss, which is something we want to avoid. So understanding how geometry affects how energy is distributed on an IoT device is helpful in achieving optimal performance for the end product and avoid issues when certification comes. So what makes for a sound IoT layout? So let's look at the big picture first. Why do we need to pay attention to the way we lay out a radio that's connected to an antenna? What do we gain or lose? So a good place to start is with what is called a wireless link budget. And you can see that represented here on the screen. Like any budget, we have to add our income with and subtract our expenditures to know if we are in the red or the black. In wireless, we add our gains and subtract our losses. So when we reconcile our gains with our losses, we have what's called a link budget. The catch with RF layout is we are unintentionally creating losses. This is something pads can help avoid. So that brings us to the subject of impedance matching. Now, for those of you not familiar with it, I'm going to give you a very simple overview and show how this relates to a link budget and how a link budget can be adversely affected by poor impedance matching. So impedance matching maximizes power transfer from the transmitter, the radio, to the antenna. Now, the radio antenna are sitting on the circuit board, and there are traces connecting the two. So it doesn't matter whether we're receiving a signal or transmitting a signal, the relationship is a converse one. And at low power levels, like we're dealing with in IoT, legally under a watt in Europe and in America, and in most of the 217 countries around the world that have similar regulatory standards, but normally we're even much less. For example, like in the Z-Wave, standard, we are very close to 1 milliwatt or 92 dB microvolts. Very, very little power. So we have to pay very close mind to how we connect our radio to our antenna. Now, this is something that scares a lot of developers. Impedance matching is not an uncommon source of consternation that are unfamiliar on how it's done or the tools commonly used. And this is a Smith chart. A Smith chart is a common tool used by RF designers to graphically represent. It can be a daunting sight to someone who's not used it regularly. It assists in solving transmission line and matching circuit problems. It displays impedances and admittances and reflection coefficients, scatter parameters, and noise figures, but it really does look very busy. So I hope I'm not losing some of you, and this doesn't scare any of you away. I know what you're thinking. He's going to show us an easier way by using pads to fix this. Well, let me say yes and no. So pads can help with the transmission line or PCB trace part of the problem, but you might want to tackle the network, the matching network as it's called, and we're going to explore Pi network today, or Smith chart, the part of AMS that I previously mentioned that will help with this. So matching again on a circuit board between a radio and antenna just means to connect the radio to the antenna in a way where there's the least amount of signal loss. And what you see on the screen right now are three very basic matching networks. They're very common. The one that has the least parts is the L, and it's called an L because it's in the shape of the L. This is a source here with the source resistance and source impedance, and this is a load with load resistance, load impedance, and we have an L matching network with a series inductor and a shunt capacitor. And here we have a pi. It looks like in mathematics the symbol for pi. And here we have a T. This looks like a T with two series inductors and one capacitor. So the one we're going to look at today is a pi. Of course, L has the fewest components. Whenever you can use an L, use an L. Why? Because it's less parts and less cost for components when the product's completed. So a pi network is a matching network, and we're going to take a look on how to check the impedance of the interconnecting traces that connect this side here and this side, one to the radio and the other side to the antenna. So as I previously mentioned, this is a very common place where designers unintentionally lose signal because the output and the input of the radio are connected to this. So although chip down and modular radio solutions are ubiquitous today, the necessity of an electrical and geometric link between the radio and antenna exists in all wireless IoT devices. So here we have a common pi matching network, which consists of 2 shunt capacitors and 1 series inductor. 2 shunt capacitors here and 1 series inductor, and this is an antenna port where the antenna connects. So this is one of the most important ways to match the radio with the antenna. One of the most critical, rather. Matched impedance allows maximum transfer of signal, as I said, from the radio to the antenna, and if not done correctly, we'll have loss. So we don't want loss, so we're going to try to avoid that by using PADS layout, a tool in PADS layout that will allow us to do this in a few different ways. So all we have to do is to select the pin pair option, which is by selecting the trace, and then right-clicking and showing properties, which we see down below here. On the next slide, you can see an arrow pointing to the impedance, which is 50 ohms. Now, there are many electrical and physical properties that affect impedance. One is the thickness of the dielectric of the circuit board, which you can enter into PADS. Another is the trace width. Another is the thickness of the circuit board, and all of the electromagnetics around the trace. This is a very simple illustration we have today, though, with just a uniform ground plane underneath of a simple 2-layer board. Just one tip for those of you who are experienced PADS users is you do have to select both the top and bottom layers as split mix planes for this pin pair property to display. So constraining the electrical and geometric qualities or parameters is another way to assure optimal impedance matching between the radio and the antenna. And here you see an illustration of parametric constraints that you can enter in Designer, where you can actually define you guys should define each trace if you want, and you can define radio and microwave stubs and links and components so that it constrains really the electrical behavior to what you've defined on the screen. It's just another way to avoid mistakes and oversights in layout prior to going into layout. So when we define our parametric requirements in Designer, they will be physically represented in PADS layout. This is one of the very helpful ways to avoid making mistakes in layout, and you're basically locking down the electrical requirements even before we get here. So next, I'd like to talk about simulation. So after we've completed our layout, simulation is a rapidly growing norm in the design cycle. The 3D geometry is exported from PADS and subsequently imported into a simulator such as ANSYS HFSS, which is my weapon of choice. So as many of you may already be aware, you can export CAD files from PADS and import them directly into another piece of software. In this case, ANSYS HFS will import it, and typically in one way you would do this. There presently is just one option. I think we have a few other that are in the works right now. Now, you might say, well, why simulate? Sometimes the visual representation of what's going on the circuit board is very helpful. So you really have some basic setup and configuration in your simulator, like with HFSS. It uses a finite element modeling using adaptive mesh and a compliant solver to render really useful information. It could save you time and money by reducing the number of design iterations prior to production. And I can tell you from having done this for 25 years, I have very good job security from fixing and addressing oversights from customers that don't use these tools and don't use all of the utilities that PADS offers to avoid some of these noise issues. So here is an IoT chip antenna. and associated PCB laid out in pads. The frequency is close to 900 megahertz. This happens to be a LoRa and Z-Wave range of frequencies. So it's simulated in HFSS after being exported by pads. So here we realize some of the limitations of very small apertures. And you might say, well, why do you say that? Well, here we have a rendering from pads, and here is the imported file from pads in ANSYS HFSS, and it's showing a dynamic animation of a far field on the bottom here, and currents and voltages here on the actual PCB. The chip antenna, which was placed in pads in 3D, was imported, and you can see it right here. But the real telling piece of information we got from this cycle from pads to HFSS is if we look down below, the peak gain that in dB is minus 3.16925. Well, we know a minus is a loss, right? So this antenna and this configuration actually serves as a loss. Now we talked about impedance matching. Now we're talking about the actual antenna itself. So both can be sources of losses or gains, and we want to avoid the losses. So that brings us to to take a look at a development tool I designed just a few weeks ago for a conference I spoke at in Austin, Texas, an IoT conference. And this board was intended to kind of be lighthearted, to have some fun with. The goal, though, was to develop or to make an IoT development board that would illustrate how simple of an embodiment a 900 megahertz IoT solution can be. And this happens to be a LoRa. It says LoRa on it because LoRa is one of those IoT standards we looked on that one slide early in my presentation. So here it is in the flesh. This is actually what the board looks like. These aren't really the best photographs, but on the one side, we have nothing but copper. And on the opposite side, we have a breakout board with a radio and a very simple interconnect, one for programming, one for a terminal program, an FTDI interface, a simple jumper, and power with a little bit of VSD protection on a USB interface. But really, the radio and sensor is on a breakout board here. It's modularized. We did this really to simplify and illustrate how you could take something like this with a simple, here's our pi matching network I explained, and this would connect to a UFL connector or to an antenna. Now this particular board, just to prove a point, what we did is we put a piece of wire antenna, 1 penny piece of wire for an antenna, and we got almost 2 miles of range with this design. Here's the schematic in Designer, a very low part count as you can see, as I've covered. We have the RF module and the breakout board. So we really don't have anything, again, more than a radio programming header, USB power, and the pi matching network that I mentioned. Here's in pads, here's the layout in pads. So we placed all the components on the bottom of the coaster, shaped PCB. So the users could use the development board as a drink coaster when they weren't developing. And actually it was kind of fun because we had the coaster sitting on everyone's desks. No one even knew it was a development board until we told them to flip it over. So very little attention, you'll notice, was given to the power and digital portion here. You can see this is really not an ideal way to lay out a board. We did it on purpose to make a point. I don't believe this, I can't remember if we auto routed this or just very haphazardly routed it, but we really just wanted to stress how important it is on a design like this to really pay most attention to the RF portion and the matching portion of the design. The top side of the board is all ground with no interconnects and no traces. This was also intentional just to fool the audience into thinking there was not a circuit board that their drink was sitting on. So the illustration of pads and impedance matching utility was actually from this design, the one I showed earlier in the presentation. You can see the pi network here again, and the one trace that we simply right-clicked with pin pairs, and we verified our impedance match at 50 ohms. So we took this coaster design and we went through the same simulation cycle I showed you earlier with the chip antenna. So we imported the coaster radio development board into ANSYS HFSS and simulate it. And here we can see that we have an impedance mismatch because we have a lack of symmetry from right to left. And so what we did is we introduced a marker that allows us to pick a frequency of interest for optimization right here. And here's that Smith chart again. So the Smith chart tool is in several simulators, and it allows us to graphically introduce the network by adding capacitors and inductors by following this frequency line here. So again, every part costs money. So on this particular first simulation, we chose just to make it work with an L-type network, 2 parts instead of 3. We created a port with an input and output that represented the capacitor and inductor of the matching network. And voila, we optimized and have a good match. Now, here's a plot, a polar plot of the simulated radiation. And you remember when I started the presentation with that orange donut-looking orb with the 2 holes in it, you can see where the nulls are right here in 2 dimensions. And of course, everyone loves the far field rendering in 3D, and this could be rotated and animated for the sales and marketing group. I don't know if we have sales and marketing people in our audience today, but the visual always helps with these sort of things. Sometimes, just to give you an example, we have developers that would like to use polycarbonate instead of ABS as a material. Radio waves don't go as easily through polycarbonate, as strong as it might be, and as resistant as it is to scuffing and to dropping. ABS lets radio waves go through quite a bit more easily, and a polycarbonate, that material, is another source of loss. So here we, again, in this 3D far field rendering, we can see the null right here, and there's one on the opposite side. And lastly, we can also have dynamic animations in our simulators. And this looks like one of those, I think, psychologist Rorschach psychology tests they give, but this is actually showing voltages around the antenna, which is right here, and the coaster board, which is right here. Okay. So that brings us lastly to electromagnetic regulatory compliance, where the last hurdle we have to get through typically before we can sell an IoT product. So the FCC is normally the first hurdle most IoT product developers have to get through. And the worst thing that we do is when we get through one of these cycles is failing at FCC and having to go back and design all over again. So these are some of the several test requirements for most IoT wireless products. We have transmitter power test. They pick the lowest, middle, and highest frequency they have to check. Worst case RF power out, the data rate is checked as well, up to the 10th harmonic. Sometimes there's preamp high pass filter testing, and all this testing is done at 3 meters in open air. So that pretty much concludes my presentation for today. I hope everyone has enjoyed it.